Alright, good morning everybody. Today is Codeforces round 665. It's a Div 2 round only, so it's not rated for me, but I'll be competing anyway. If you'd like to see my thought process during contest, you can watch me compete. It'll be here. If you're just interested in the solutions, though, I'll have those at the end of the video. So there should be timestamps in the description if you want to skip to a particular problem. Otherwise, you can just watch solutions to all the ones you're interested in. And yeah, we'll see. Good luck, have fun to everyone who's competing. Looks like all the problems are unique, so there's no like part 1, part 2.
Moderate rain with 82% humidity and a high of 67 degrees.
We have company. We have company 0. Oh, did I forget to register? Oh man, I forgot to register. Well, I think that's fine. I'll just have to submit everything 15 minutes in. Alright, distance and axis. We have a point with coordinates x equals n on the x-axis. We want to find an integer point b such that the absolute difference between O and B and the distance between A and B is equal to k. It has to be an integer point. So parity has to match, I think. So the biggest it could be would be k. Yeah, so the distance, so n has to be at least k, or bigger than k, but the parity has to match. So that's parity matches. This you take 3 steps to get to k. This is 1,000 steps. That's 1 step because parity has to match. Yeah, okay. So into n equals this, k equals this. If n is greater than or equal to k, this out n minus k mod 2. Otherwise, this out k minus n. So I forgot to register, which unfortunately means I can't submit. I don't think I can submit, at least. Maybe I can. Yeah, okay. So we'll just have to submit A, B, and C like 15 minutes in or something. All right, you're given 2 sequences, this and this. Oh, we should just run samples to make sure that's right. Zero 3 1,000 or something. 0 1 0 looks good. All right. Problem B. You're given 2 sequences, this and this. Each element in both sequences is either a 0 or a 1 or 2. The number of elements 0, 1, and 2 is equal to x1, y1, and z1 respectively. The number of element, oh wait. Yeah, okay, so you know how many A's or how many zeros are in A, how many ones are in A, same thing in B. You can rearrange the elements in both sequences if you'd like. However, after that, let's define a sequence C as follows. A times B, if A is greater than B. 0 if A is equal to B. Interesting. Well, what can we do? We can do, so 2, 1 will give us 2. 2, 0 will give us 0. 2, 2 will give us 0. 1, 1 will give us 0. 1, let's just do this in order. 1, 2 gives us -2. 1, 1 will give us 0. 1, 0 will give us 0. And then 0, 2 will give us 0. Same thing with any of the other ones. So it looks like the only things that matter are 1, 2 and 2, 1. So every one of theirs they have, we want to place it with one of our 2's. Yeah, interesting. Okay, so first we want to place as many 2's with their 1's as possible. Then afterwards we want to place 1's with their non-2's. And then it doesn't matter. Yes, that's just what we have to do. Okay. So let's look at samples, I guess. 2 2's, 3 1's, so we can do a 4 there. Plus we can match this with anything else, so it's just 4. Here's a 2 with a 1. Yeah, that's fine. Yeah, okay. So samples aren't great, but that should be fine, I think. Alright, so int a0 equals this. Well, let's just say int array a equals fs start read array 3. Array b equals fs start read array 3 as well. Score will be math.min of the number of 2's that we have and the number of 1's that they have. Yeah, so now there's no difference between our 1's and 0's. So a at 0 plus equals a at 1. A at 1 equals 0. And now we want to match as few 1's as non-1's as possible. Int sub will be b at 1 or a at 0. This is, I guess, to remove. Oh, there is a difference between these two. This isn't a at 0. This is now a at 2. And the number of points we lose will be math.min of b at 2, a at 1. I think that math checks out. All right, so let's try the one other test case, which would be we have 0, 1, 0, and then 0, 0, 1. So now we should get -2 points. Yeah. We can't submit. All right, that's fine. Let's move on to C. You're given an array where you have a bunch of integers greater than 0. In one operation, you can choose 2 different indices, I and j. If the GCD of these 2 elements is equal to the minimum element in the whole array, you can swap these 2 elements. Now, you'd like to sort A using the minimum number of operations. Or using the operation any number of times, never mind. Determine if you can sort it. So if it's already sorted, you're good. If it isn't already sorted, then you need the GCD of the array to be the smallest element of the array. That's not true. There's some elements you don't need to swap. Like, you might have some elements at the end of the array that you can just leave there. Those elements you don't need to consider in the GCD. So if you've got like a bunch of elements like this, you might have some big things here, but you never have to swap them, so it doesn't matter. So now these things, like you need to swap this element to get it to the end. That means this thing needs to move. We want to check if this GCD is equal to the smallest thing in the array. So we can always do this. We could swap these 2. Then we could swap these 2, and we could swap these 2. So now we figured out a way of doing it. So I suppose we don't necessarily need the GCD of everything. We just need whatever, so we need the smallest thing in the array. And then we also need everything that's in the wrong spot. And if all of those work, we're good. So that should be fine. Good. All right. So int n equals this, int array a equals that, int array sorted equals arrays.clone, or equals just a.clone. And we want to ruffle sort. People always ask me what ruffle sort is, and it's just calling arrays.sort, but it shuffles it first. So like ruffles it up and then sorts it. And it does that so that you can't break it with the n-squared quicksort case, because arrays.sort uses dual pivot quicksort, which can be n-squared worst case. So that's why you have to shuffle it. Alternatively, what I used to do is put it all into an array list and then sort the array list with collections.sort. That works too. Yeah, okay, so int min equals sorted 0, I equals 1, or I equals 0, as opposed to 9 plus plus. If a at I is not equal to sorted at I, then we need to swap these two. So if a at I mod sorted at I, or mod min is not equal to 0, then this out no, I think, and then continue outer. Otherwise this out yes. All right, looks good, and we can register now. Wait, hang on, how do I register? Should be able to register 15 minutes in. There we go. Register. Thank you. And now submit. There's C. Here's B. Here's A. Maximum distributed tree. You're given a tree that that consists of n nodes. Man, I don't know why my bot isn't working for some reason. Did I get them? I did get them. All right. Yeah, you're given a tree that consists of n nodes. You should label each one of its n-1 edges with an integer in such a way that it satisfies the following conditions. Each integer must be greater than 0. The product of all n-1 numbers should be k. The number of ones among the n-1 integers should be minimum possible. Okay, let's define f whatever as the sum of the numbers in the simple path from u to v. Also let the sum of, for all pairs, you find this thing. This is the distribution index of the tree. Find the maximum possible distribution index you can get. Interesting. So, yeah, that's kind of a cool problem. So for each edge, all that matters, since we're summing it, all that matters is how many times is this edge counted. And all that is the number of things on the left side times the number of things on the right side of the edge. So we have all of the values of our edges. Is OBS still alive? Come on, computer. You can do it. All right, we are fine. Oh, I see. Interesting. We're given the prime factorization. We print the answer under mod. Yeah, so I think we just need to know how many times each edge is counted. We know how many things, like, they want the number of ones to be minimal, right? So we only get to merge some prime numbers. We don't get to merge all of them. Because if we could merge all of them, we would just multiply them all together and use that for whatever the biggest edge is. But we have to keep as many of them, we have to keep lots of them. So, yeah, so we'll merge them, we'll merge as many as possible, that is, into a single edge, and then use the rest of them on different edges. Yeah, that's fine. Okay, sure. So we're gonna need a node, and we're gonna need a array list node adjacent. We'll need the subtree size. What else? Yeah, I think that's it. So DFS, pass in the parent. This dot subtree size equals 1 for node nn and adjacent if nn is not equal to the parent. Then nn.dfs, with me being your parent. Then this dot subtree size plus equals nn.subtree size. Okay, that does that. Static, well, good. All right, so now it is multitask case. We've got the number of nodes in the tree. Yep. Factors was this thing, I think. That's what they said. Oh, just n. Okay, yeah. So we've got all the nodes. We can read them in. And then we want to add all the edges. Okay, so then we read in the number of prime factors. Then we need to read in what those numbers are. It's probably helpful to have those sorted too. Then what? Well, then we need to combine them into a new array. So, yeah. So long array values equals new long array n. So if number of primes is less than or equal to n, we do one thing. Otherwise, we need to combine the last one. For I equals n. equals n primes minus 1 greater than or equal to 0 minus minus values at values at n primes minus I minus 1 will be equal to factors at I. So now we have these sorted in descending order. Otherwise, we need to combine them. Yeah, okay. 4 into I equals n primes minus 1 is greater than or equal to 0, I minus minus. Int index will be math.max of 0, and n minus I minus 1. Okay, now values at index equals values at index times factors at index, or at I. Alright, so now we just need all of the edges. Okay, this is n minus 2. So that should be fine. New long array n. Well, then we need to do our DFS, so nodes at 0.DFS. Then we need to count each edge amount. So the number of times it'll be used will be nodes at I dot subtree size times n plus 1 minus nodes at I dot subtree size. Edge weights at I minus 1 times. And then we need to ruffle sort that. Oh. Okay, now we just need our answer. Yeah. 4 and I equals 0. Less than n x plus. X plus equals multiply the edge weight at I by the values at n minus 1 minus I. Alright, so let's see if we understood the problem correctly. 17, 18, 2, 8, 6. Yeah, I think that's fine. I don't have any problems with that. I don't think. But we'll see.
Wrong answer, test 3, sir.
Interesting. Interesting. So reread the problem. You're given a tree with n nodes. You should label each of its n minus 1 edges with an integer such that each integer is greater than 0. The product of all integers should be equal to k. The number of ones is minimal. Then you want to find the maximal distribution index you can get. So the distribution index is sum of numbers along a path. So let's look through this code again. We have a bunch of nodes. We read in all of the nodes. We go from 1 to n, read in a and b at the edge. Then we have a bunch of primes. We read in the primes and sort them. Okay, then we have a bunch of values. If the number of primes is less than or equal to this, then we just set it. I guess we don't even need this special case. Oh, I'm stupid. Yeah, okay. Alright, so now, well, we've cleaned this up a bit, but now we need to ruffle sort this and just make this I.
Wrong answer, test 3, sir.
Wrong answer again, huh? Subtree size times, this is the number of nodes minus the subtree size. That's the parent edge, yeah. The parent edge has this many things in its subtree, this many things out of its subtree. The sum of m over all test cases is small. Why does that matter? I must not be understanding something. Why would this constraint matter? That means my solution path is wrong. Oh, maybe it doesn't. Wait, are these the samples? That's the first test case, that's the second test case. What's the third test case? I guess it's 7 nodes, so it might be a little bit better. But it's just going to be the... Well, no, it's not. This is 10 to the 10 times 10 to the 4. That's 6 times 10 to the 14. That should fit in the long. Why is this wrong? Alright, so we've got this tree, which we build. Then we DFS. And we go through everything that isn't the root of the tree. That parent edge will be the subtree. Like, it'll split it into the subtree and everything else. Here are the number of things on one side of the node. Is this some weird? It's just the number of things on one side times the number of things on the other. Each time we go either one way or the other. So yeah, that's the number of times each edge is counted. The subtree size plus everything minus the subtree size, right? The number of the edge weight here will be equal to the number of times it's crossed. Sort the edges, sort the values. Multiply this edge weight by this value. Well, let's try and break it, I guess. Maybe we do something like this. So the edges we have are 1, 2, 2, 3, 2, 4, 4, 6, and 4, 5. Then maybe we just give one number, and that's a 2. We need single test case. That's fine. Let's try again, maybe. 38. It sounds plausible. So 9 with 2. Recross this 9 times. 1, 2, 3, 4, 5, 6. Yeah, I buy it. Then the rest of these are apparently 5, which is 1 times 5. Okay. Two, 3, 5, 7, 13. Hopefully that's 11 times 13. I think so. 143, yep. Ah, I'm an idiot. Ah. Man, I'm so silly. I was looking at this for like 20 minutes too. It's just a basic. See, I even wrote the mod function, I just didn't write the add function. So close. All right. Looks like E comes next, but E is a bit more tricky. So here's where the problems actually start. Divide square. There's a square of size 10 to the 6 by 10 to the 6 on the coordinate plane with 4 points. Yep. You're going to draw segments on the plane. All segments are either horizontal or vertical and intersect at least one side of the square.
Wrong answer. ACA problem D.
You're wondering how many pieces of the square divides into after drawing all segments. Write a program calculating the number of pieces of the square. There are no two segments on the same line, and each segment intersects at least one of the square's sides. Yeah, okay, that's an interesting problem, I think. It's pretty cool. So 1, 2, 3, 4. Yeah. So there's 7 like that. Good. Yeah, I think that's a cool problem. I don't know how to do it. Reverse and swap. You're given an array of length 2 to the n. You have to process q queries on it. Each query is 1 of 4 times. Change this thing to k. Or reverse each subarray. Oh, whoa. This seems not too bad. This seems like a segment tree problem. Or maybe like a fancy tree problem. Yeah, this one seems doable. All right, let's focus on this one first. I think this one's easier. I think like I could definitely do it at least. E, I'm not totally sure about. Oh, maybe scoreboard disagrees, but scoreboard disagrees pretty strongly, actually. Yeah, okay, well, let's think about this then. We have a square of these sides. We want to draw a bunch of line segments, each are either horizontal or vertical. How many pieces does the square get divided into? What if we did like a horizontal sweep? We had like a vertical scan line, went left to right. Then every time we have one of these lines, I think we just want to arrange some. We kind of want to arrange some. So here's the idea, like we've got this grid. And we have a bunch of horizontal lines in the grid. So then we'll have an imaginary vertical line that sweeps across. And then when we get somewhere, we see a vertical line. And we see this one. Then we want to count this. Let's imagine this went farther down. Then we would also count this. Yeah. So I guess we'll consider this range between these two here. How many times does it get counted is what we're interested in. But it's also possible that we want to count this one as well. So it's like when we see this line here, then we have to activate this. Yeah, I think that's the idea. So we keep track of which lines are alive. Initially, we have this one, this one, this one, this one, and this one. And then when we get here, this one gets deleted, so it's no longer alive. So then if we have this, the range sum here is 3, which means we add 1 for this, add 1 for this. Then when we get here, we've deleted this, so now we have a range sum of 2, so we add 1, or range sum of, yeah, so we add 1 for this here. Then we see this, but nothing happens. So the next time, if we have this range here, we need to process all of these things that are like in the queue of like need to be added. So I think we need like a tree set of those. Once we add it, then it'll be part of this Fenwick tree, and then later on we can use it. Yeah, okay. I think that's fine. Sounds good. All right, yeah, this is problem E. So we're gonna need this Fenwick tree a bit. Then we'll also need some events. So we need an X that it occurs at, also a delta, or I guess a type. Well, let's just make it a delta for now. And then int y1 equals -1, int y2 equals -1. So if the x's are different, sort by x's. It's possible they're not, though. In which case, it depends what we want to do. Is it possible they don't intersect at an edge? Because that would be very convenient. Yeah, okay. So it's not true. So what does that mean for us? We want to, yeah. So if delta is not, or if delta, oh wait, do we just want to sort by delta? We'll just make the delta 0 for the queries. For everything else, we want to add first, then process queries, then remove. So return negative integer dot compare delta dot delta. Yeah, okay. Sounds good. Is this multi-test case? It's not. And segments. Oh, they give us horizontal then vertical even. So nice of them. All right, I'm gonna go to the bathroom, but I will be right back. So the thing I'm thinking about is why there's this constraint that it has to intersect the square. Because I don't immediately see how my solution would fail without that constraint. In fact, I'm pretty sure it's right even without the constraint. So I'm not going to worry about it for the moment. And then I'm just going to type it up, and if it's wrong, then we'll think about it for a bit more. All right, that's fine. So, yeah, so we have the number horizontal, number vertical. Now we need to read them in. Then we want to sort this list. Then y equals this, x1 equals this, x2 equals this. Events dot add new event. So the x will be, so we're gonna add two events here. X1, the delta will be 1, the y will be this, y2 will be, I guess, just that as well. Then we also decrease by 1 at x2. So x2, yeah, they're different. And we've got this many vertical segments, so we're given x and then the two y's. First we're given x, then y1, y2. We just have one event here. Got a delta of 0, happens at this x. Alright, so now we need a tree set, integer. Yeah, this will just be to add. Oh, I guess it's more of a map than a set. Okay, static. Oh, that's annoying. Well, I guess it just, maybe the endpoint thing just makes it easier. So that we don't have to handle this case, we can just use a priority queue. Yeah. Well, let's just do a tree mat for now. Wait, no. No two segments are on the same line, so a tree set's fine. So now we need to go through each event. If this event starts on the left endpoint, then we don't care. We also need a bit. So update position 0, by 1. Update position 10 to the 6th by 1. Range sum would be nice. So then, oops, we only do these once. For each event, okay, if b dot delta equals 1, if e dot x equals 0, then just do it. Otherwise, we need to add it to the no endpoint list. No endpoints dot add e dot x or e dot y by 1. Otherwise, bit dot update e dot y1 by 1. Okay. Else, if e dot delta equals -1, then it depends whether or not this has been added. So if, well, maybe it doesn't depend at all. Yeah, I guess this isn't super important. The endpoint's -1, we can just delete it in this case. Then bit dot update e dot y1 by -1. Otherwise, it's a query. So now int n intersect will be bit dot range sum from e dot y1 to e dot y2. Parts equals 0, it's a long. Then parts plus equals and intersect -1. This is out parts. And then finally, we need to look at the no endpoints. Well, I guess it depends which side this is, right? So if e dot y1 equals 0, otherwise do something else. If y1 is 0, then we check the smallest thing. So while not no endpoints dot is empty, and no endpoints dot first is less than e dot y2. Then int first equals no endpoints dot first, no endpoints dot remove first, and then bit dot update first position by 1. Okay. Dot last is greater than or equal to, this should be less than or equal to e dot y2, this should be greater than or equal to e dot y1. Good. So I think that's it. Not even close. Alright, well, let's see what's happening. Test this out. Processing this event. Processing E. We need E.toString. Okay, so x equals 0, y equals 4, and then y equals 3 as well. Y equals 3, delta 1. Now x equals 2, y equals 0, or from 0 to 5. So 0 to 5, that should intersect 3. Yeah, intersects 3, that's right. So that adds 2, 1, 2. Oh, am I off by... I'm off by 1. Wait a minute. I guess if I just add a full vertical line here, that'll fix it. Because I'm off by 3. 1, 2, 3. So if x2 equals 10 to the 6, and x2 plus plus, and also n vertical plus plus, then also events dot add new event from 10 to the 6. That's the x, the delta is 0, the y1 is 0, y2 is 10 to the 6. Okay, that makes sense. This would be nice to have for sure. Let's try this. Good. Alright, maybe let's try problem F then, because what else is there to do? I don't think problem F should be too bad. I read it earlier, I had an idea immediately, and it's got several solves. It's got 40 solves, so we should be able to do it. How are we looking on the scoreboard? 70th place? Yeah, not the end of the world. Not too bad. D. Oof. Yeah. D was a bit annoying because I forgot to add, or I forgot to mod after adding. That's fine. All right, problem F. You've got an array of length 2 to the k. You should process a bunch of queries. So either, let's see, what do these actually mean? You change this position to x. That's really easy to understand. This is, you print the sum of these elements. That's also easy to understand. So what do these two things mean? Okay. So reverse subarray. So you pick some power of 2 size, and then you reverse each subarray of that size. Okay, I think I understand. Swap subarrays. This mean go like that. Yeah. So swapping the subarrays, I think, isn't too bad actually. If we, I think we can just turn the swap subarray into 2 of the other query. So what does that look like? Or I should stop drawing it like this maybe, should I? Yeah, I guess that's fine. So yeah, I think the swap is pretty easy. So I didn't think about this earlier, or this swap part at least, but. So here's the idea, I think, for the swap. If we reverse this, so now we go like this, that's the first part, here's the second part. We reverse that and then reverse that. If we do that after we do this, 1, 2, 3, 4, then the things we'll get will be, initially it was 1, 2, 3, 4, 5, 6, 7, 8. That was the initial order. After doing both of these, then we have 3, 4, 1, 2. 7, 8, 5, 6. Yeah. So any swap we can just turn into 2 reverse of a given array. So that's fine. So now we have one query type, which is, it's just reverse it. So just like reverse powers of 2. It's like power of 2 blocks. That's the only thing we actually have to do. And I think we don't even need to actually like update that. We can just ignore that we have to do that, and then store like a global array somewhere of whether this layer is reversed or not. And I think that's all, that should be fine. So if I'm understanding the problem right, this is actually quite easy. Maybe let's work through samples before committing, because if I'm understanding the problem right, that should take like 20 minutes to code. So let's just make sure my understanding is fine before I type it. So initially, this is the array. We have 3 queries. Type 1 is change element 2 to an 8, so this becomes an 8. Then type 3, swap swap the things of length of 1. So you swap these 2, I think. So it should be 9, 9, 8, 8. Then find the sum from elements 2 to 4. So 9 plus 8 plus, or 9 plus 7 plus 8. That's 24, yeah. Yeah, I think that's fine. Let's code it up. This is really a seg tree array would probably be easier in this case. Well, let's just do the classic. So the mid will be leftmost plus rightmost over 2. Kids at 0. There's a new seg tree from the leftmost to the mid, level -1. Same thing with the kids 1. It goes from mid to rightmost. Rightmost. All right. Yeah. We probably also want to pass in the array. And we need the sum. So pass in the array to the kids here. Public void recalc. Yeah, then recalc. Otherwise, the sum will be equal to a at leftmost. Sum equals 0 for seg tree s in kids. Sum plus equals s dot sum. All right, so now we have our new sum. Public seg tree l child, and we also want one for our child. Then we'll have a static Boolean array. Flipped. New Boolean array 20 or whatever. Well, we'll just leave it for now. So if flipped at level, then return kids at 1. Otherwise, return kids at 0. The right child will just be the same thing but backwards. So now we can get our left kid and our right kid. So now we have public void point update. In index in value, recalc at the end. If leftmost equals rightmost. Was it set or add? Replace it with k. Then sum equals value. Return. Otherwise, if index is less than, yes, this is a bit messy. But if index is less than 1 left shift level -1. And L child point update the next value. Otherwise, index minus equals 1 left shift level -1 and our child dot point updates this index's value. Okay, public void range sum int L So if L is less than or equal to 0 and R is greater than or equal to 1 left shift level minus 1. Return sum. No long. Okay. That's if it covers me completely. If L or if R is less than 0 and or L is greater than or equal to 1 left shift level, then return 0 because it's outside my range. In other case, it splits me. So in that case, long L sum equals L child dot sum or dot range sum from L to R. R sum will be R child dot range sum from L minus 1 left shift level minus 1 to R minus that thing. Then return L sum plus R sum. Okay. And log n equals this. Flip equals new Boolean array. Log n plus 1. Seg tree st equals seg tree from 0 to 1 left shift log n. The level will be, what is the level? I guess the level is log n. And the array will be the array. Array A equals fs.readArray log n. How much time do we have? 30 minutes. What? So much time. I expected to have like 10 or something. Excuse me. That's fine though. We also need the number of queries, which we haven't read. Now we need to answer all the queries, right? Yeah. For query Q and queries. What am I doing? For int Q equals 0 plus the number of queries plus plus. So then we've got some types. So if the type is equal to 1, otherwise if the type is equal to 2, otherwise if the type is equal to 3, otherwise if the type is equal to 4. Well, the type equals 1 should be pretty easy, right? That's just segment tree dot point update. So it's just st dot, well, okay, so index equals this, value equals this. Index should be 0 based. St dot update this index to this value. So that's easy. This should also be pretty easy. Yeah, okay. So now we just have these two queries, which are very similar. So reverse of k or swap of k. So all of this is, if I'm understanding this correctly, is flipped at k, x equals true. I think that's it. This is reverse, right? Yeah, this is reverse. and this is swap. So this is just the same thing, but with a minor modification. Let's just flip it k minus 1 XOR equals true as well. Wait. Oh, this is really k plus 1. It's k plus 1 and k. Yeah. Okay. Are we right? Nope, not even close. X2 out of bounds for length 2. Yeah. 1 left shift log n. And this should just be log n. No, log n plus 1. X4 out of bounds for length 4. Oh yeah. This is this minus 1. Unresolved compilation issue. $24. 29. Ooh. Good. Well, it's broken. How much time? 25 minutes. All right. Let's draw it out. Well, maybe it's probably helpful to print the array after each step, huh? So initially it's that. The first thing we do is we sum from 3 to 7. 1, 2, 3, 4, 5, 6, 7. So we get that right though, right? The answer is in fact 29. Okay. Then we two of power 1. So we reverse everything of size 1. This looks right. Okay. And then after that, we swap everything of size 2. 2 to the 2. So we swap the first half and the second half. Wait a minute. Yeah, this isn't actually right. Yeah, okay. I think it's like that actually. Because the flipped is just whether we flip each layer. Okay, well, closer, I think. Do we pass this first one still? So, what are we looking at here? Initially we start with 7, 8, 8, 7, 0, yeah, this is right. Then after the first so that was after the first operation. Then the second operation is reverse everything of length 2. Wait a minute. So we reversed everything that's of length 2 to the 1. So length 2. I equals 0, I is less than or equal to k, I plus plus. Flipped at I. I'm an idiot. Yeah, okay, that seems fine. So now 3 is swap everything. Yeah. Okay, so that was, yeah, could have been better, I guess. But that's fine. Print writer. (29, 22, 1). Looks good. Let's check this just for sanity. 24 also looks good. Submit problem F.
Well done, sir. AC1 cloud back.
Alright, so not bad. Interesting set. I liked it. Yeah, I don't really know that I have, I guess, what were these problems? Distance and axis, it was fine. Not particularly great, whatever. Ternary sequence. Yeah, I think that was pretty cool. It's a pretty cool D. It seemed kind of hard initially, but then like when you think about it, it's like, yeah, it's not actually that bad. So I think that's like a cool problem. I like that, those sort of like solution pads. Problem C. Oh yeah, this was good. C was very good. I enjoyed that problem. What was D? Yeah, I don't know. I guess D was okay. I thought it was pretty obvious what to do. So I don't know. But E and F were both very cool. They're both good problems, I thought. Very good. All right, let's do solutions. Solution time. Problem A. So let's get out the whiteboard. In problem A, you have 2 points, one of which is at the origin of the number line. The other one is at some other given position. So you've got this origin here, this position here. You know the distance apart is n. And you want to make it so that you can find some other point here, maybe this point here, where this is some integer. So this is some integer a. This is some other integer. Maybe it's some integer b. And you want the absolute value of a minus b to be equal to k. That's what your goal is. So this might not always be possible, but you're allowed to move this point by 1 unit, or you're allowed to move, sorry, not that point. You can pick any point you want for this. You're allowed to move this point by 1 unit, either left or right, for a cost of 1. The question is, what's the minimum amount you have to move this point for the difference between these for it to be possible that it's k? So I guess there are a couple observations. The main thing is, what values can the absolute value of a minus b even be? Well, if you pick this value here, then you can do n. So n is pretty easy to do. And it should also be pretty clear that if you pick something over here, then you've increased a by a certain amount, but you also increase b by the same amount. So if you pick anything outside of this range, the absolute value of a minus b will still be n. Which means the only part that's interesting that's left is, what about the positions inside the array? So if you move it over by 1 point, that's the smallest you're allowed to move it, then you add 1 to what a is, you subtract 1 from b. In other words, you'll change this difference by 2. You subtract 2 from it. So you can keep doing that as many times as you'd like, which means the parity of n and k have to match. So if like n is less than k, then, or if n is bigger than k, and they're the same parity, then you can do it instantly. If they're different parities, you have to move this over by 1, then they'll be the same parity. The only other case is, what if k is too big? Well, if k is too big, the points have to be at least k apart. So then the answer is just k minus n. What does the code look like for that? Well, it's pretty simple. They're just the 2 cases. Here's the case in which they're already far enough apart. You just have to move it over by 1. This is the other case. It's just k minus n. All right, that's problem A. Let's move on. Problem B. You've got these 2 arrays, A and B, and you want to maximize your total score. But the thing is, the arrays are very big, so you can't actually iterate through every element in the array. Otherwise, you'll TLE. Because they don't really bound it over multiple test cases, which means the total number of things might be about like 10 to the 12, the total number of elements in all arrays over all test cases. So you can't iterate through all of them, which means you have to find something a little bit faster to do. And you can make some observations. Let's look at this cost function a little bit. So if we match a 2, if we have a 2, like this is the thing in array A, and this is the thing in array B. If we have a 2 and a 2, that gives us 0 points. If we have a 2 and a 1, that means A is bigger than B, so we get 2 times 1 points. We get 2. If we have a 2 and a 0, we get 0 points. Then there's some more cases as well. If we have a 1 in A, we might also have a 0 in A. So if we have a 2, 1, 0, or we could have 2, 1, 0. Obviously, if we have a 0 in A, then this is 0 times 2, so this is 0. This is also 0 times 2, which is 0. And then these are the same, which means it's 0. So these are all 0. So these are like pretty much unimportant, I guess. And then for if a is a 1, this value here will be -2. Since they're different, a is smaller, you multiply them together and make it negative. In this case, it'll be 0, so since they're the same, in this case, it's also 0. So once we've drawn this out, we've noticed there are only 2 different combinations that actually give us a non-zero total, which are if we have a 2 and a 1. So basically what that means is we want as many 2s as possible to match with 1s on their side, or as few 2s as possible to match with 1s on our side. So first we want to prioritize, like it doesn't matter the order that you prioritize these first 2, but basically you want to prioritize this pair here. You want to get as many of these as possible. And then after that you want to get as many of these and as many of these as possible. Or sorry, yeah. As many of their 2 and your 2, I guess, that works. Or as many of their 2 and your 0. So these 3 red things that I've circled are all like good. You want to get as many of those as possible. So if you do this one first, and then this one second, that's your second best thing, that's your third best thing, that works. Then you can just count up how many times does each pair occur. If you think about the math for a little bit, it turns out this winds up working. So I'll kind of explain how this math works really quickly. So first I match up all of my 2s with all of his 1s. And then I remove those from the counts of my 2s and his 1s. Then everything I have left that isn't a 1, I'm going to pour into trying eliminating his 2s. Because I don't want to match my 1s with his 2s, because that costs points. So I pour all of those into my a at 0 category. And then I subtract out as many of his 2s as possible. Then the rest of his 2s that are left that I can't otherwise get rid of, those have to match with my 1s, and I lose that many points. And then it's like a ×2 multiplier for everything. So I multiply by 2 at the end. All right, cool. Let's move on. That's problem B. Problem C, mirror array. What was this one? Oh yeah, you want to sort the array. So this was pretty cool. I enjoyed this problem. I didn't think it was obvious at first, but I thought it was like an interesting problem. Seemed pretty unique. So here's the problem. You have some array, and it's not initially sorted, but you want to make it sorted. The only operation you can do is you can pick 2 elements in the array. If their GCD is equal to the smallest element in the array, then you can swap them. If it isn't, you can't change them. So there are a couple observations. The first is there are a bunch of elements in the array that might be in sorted position already. If that's the case, we can just ignore all of those elements. So if those 3 elements are all where they want to be, we can just ignore them and we're fine. What about the elements that aren't? So maybe the rest of the ones I've circled aren't in sorted position. Now, I said we can ignore the elements that I crossed out, but that's not totally true. If one of them is really small, maybe this number is a 1, then it matters because this might be the smallest number in the array. So whatever the smallest number in the array is still relevant. So we'll find whatever the smallest thing is, and then once we have it, we can only swap 2 elements in this array if their GCD is equal to this. So here's the way we can do that, which is pretty interesting. If we want to swap these 2 elements, it's possible this is like 3 or this is like a 6 and this is a 3, right? And if we want to sort them, then these need to change positions. So maybe the 3, if it's in its sorted position, is here, so we need to be able to swap it. So what we can do actually is we can swap the initially we have 6, 3, 1, right? Well, this 1 wouldn't be in sorted position at all. If it were a 1, it would be over here. So let's imagine somehow it's over here. Or, like, yeah. Let's imagine we have a 1 here, and then at the end we'll swap the 1 with this thing here. So maybe it's like a 1 and a 4. So here's the subarray we're interested in. The 1 is relevant just because it's the smallest thing in the array. So even if this were some other place, we would just find it and say, okay, this is the smallest in the array. So now, what we want to do is, in order to swap the 6 and the 3, initially we have 6, 1, 3. You can't directly swap 6 and 3 because they're not coprime. They don't have a GCD of 1. but you can swap 6 and 1. So now we have 1, 6, 3. Now you can swap 1 and 3. So now you have 3, 6, 1. And then you can swap 6 and 1 again, and you have 3, 1, 6. So by doing this, you can sort the array. Yeah, that's it. So basically, anytime you have two things, if they're both factors of the smallest number, that means you can swap them. You can put them anywhere else in the array you want. You can replace them with the position they're supposed to be at. If they aren't factors of the smallest number, then obviously their GCD won't include the smallest number, or their GCD with anything else won't be the smallest number, because the smallest number isn't even a common divisor of it. So you can't swap it if it's not a factor of the smallest number. So all you have to do is find the smallest number in the array, then find all positions in the array, and check for each position that doesn't match where it's supposed to be. You just check, is this number divisible by the smallest number? And that's it. What does the code look like for that? Well, since that's it, all it is find the minimum of the array. Then I have a sorted version of the array and the original version as well. If this doesn't match, then I make sure you can move this place to the correct position. All right, problem D. Yeah, so this problem's pretty easy, I guess. So, well, I guess, I don't know, maybe it doesn't seem easy, but it's like all of the steps you need to take are very straightforward. Like there's no, what should I try and do next? It's all just like what you would think you should, the path you think you should go down is the path you should definitely go down for this problem at least. So, yeah, okay, so the statement says you have some tree and you need to distribute factors of k among all of the edges of the tree. And the number of times each edge is counted is the total number of nodes on one side times the total number of nodes on the other. And you want to maximize the sum of the values of all edges. So I guess what they say is a little bit different, but it's pretty much the same, which is if you have some tree like this, you've got a bunch of edges. If we consider this edge, the totals we're trying to maximize are for all pairs, find the path, then find the sum along the path, and then add that to our answer along all paths. Well, we can just look at for some edge, the number of times this edge is counted is this subtree times this subtree. So yeah, we have a bunch of edges, and then we want to distribute factors of k among them so that the product of all edges will equal k. Now, if we had no other constraints on the problem, whichever edge is counted the most is where we should just put all of our factors. Because it's never helpful to split up factors. We want to keep the factors together because they multiply together, so they get big very fast. Whereas if we split them up into two things, like they only add twice as much. So it's beneficial to keep the factors as condensed as possible. You want to put as much resources into a single, min-max it, right? Like how you optimize your life. You put as much resources as possible into being really good at a single edge, whatever edge is most important. So in this case, this edge is probably most important, right? This has a usefulness of 6. So this gets counted 6 times because it's 2 on one side and then 3 on the other. This gets counted 4 times, 4 on one, 1 on the other. This gets counted 4 times as well. This is also 4. So yeah, okay. So that's like the solution. But there's one other caveat, which is the numbers have to multiply, they have to multiply to k. But also, you want as few ones as possible. You want as few edges as possible to have the value of 1. So basically, what that means is when you have your prime factors, you can't just put all of them together. Instead, you have to leave a bunch of them separate so that when you put some together, you just have one big number, right? So let's say you've got these 4 edges and your numbers are 2, 3, 5, 7, 11, and 13, maybe. Then for the worst edges possible, you'll give them these bad things. So you give this, it can't be a 1, right? So you give this 4 the thing that's crossed 4 times a 2. You give this thing that's crossed 4 times a 3. This is the next worst edge, so you give it this 5. Then you have this really good edge. You want to give it as much as possible, so you give it everything you can. So that's how you distribute the prime factors. I guess the last question might be, how do we figure out how important the edge is? Like in code, how do you actually do that? Like I've explained, it's just the number of things on one side times the other, but that might be kind of tricky. So if we root the tree arbitrarily, I guess this is what this tree, let's say we root it here. Then it would look like that. There's this tree. So if you look at all nodes except for the root, all of them have some parent node. And you, like the size of the edge, like the value of the edge, let's consider this edge here maybe. What it's going to be is just the sum, like the number of nodes in this subtree times the number of nodes not in this subtree. The number of the nodes in the subtree we can pre-compute with the DFS. The number not in the subtree is n minus subtree size. So it's this times the subtree. That's just the value of this edge. All right, yeah. So what does that look like in code? Not too bad. We have a bunch of nodes. We add all of our edges. We read in the factors, and then I sort the factors smallest to biggest. Then I have a bunch of, these are the values that I use, and these are the values of, again, the values of these particular edges. So like the smallest one will be 2, then 3, then 5, then the product of all the big things. Alternatively, if you don't have enough, right, if your only prime factors are like 1, 1, 1, and 3 or something, then it'll look like that. Then you'll just put 3 as the biggest, and then everything else will just be 1s, because they're forced to be 1s. So you can find the values of all of these things, and then this just multiplies them to combine them all in one index and put everything else in the rest of them. And then I sort this array. So this will be actually sorted in decreasing order, or not necessarily decreasing order, but in like some order. And then I sort that at the end. Probably makes more sense to put that code up here. That way it's like self-contained. Then for the edge weights, first I do a DFS to calculate the subtree sizes. Then for each node, it's just its subtree size times n minus the subtree size. This plus 1 is because I subtract 1 from here, so from here on, n is just the number of edges, not the number of nodes. And at the end, I just multiply them all up and add them up. Don't forget to mod, ladies and gentlemen. That is an important, or a common error at least. Okay, yeah, I think that's it. That's problem D. 2 more problems, problem E and F. We'll look at those real quick. Problem E is a pretty cool problem. The idea is, or the question is like, you have some big square like this. You want to count how many, and you also draw a bunch of lines in the square where each line touches the edge of the square in some way. So maybe you have something like this. Now the question is, how many pieces does this divide the square up into? In this case, you have 1 piece here, a second piece here, third one here, fourth one here, fifth one here, sixth one here, and seventh one here. So here's the solution to the problem, I guess. When you have all these lines, we're going to do a sweep from left to right. We're going to keep track of like a vertical scan line. And we're going to keep track of like, what do the horizontal lines look like as we sweep left to right at this x coordinate. So I'll use the same example here, and I'll just draw in the horizontal lines first. So initially we have something that looks like this. We also have this, we've got like, this is the top, right? So here's the top, and here's the bottom. So what we're going to keep track of as we do this sweep are what are the lines that have like a bound on the right side. And then, yeah, we'll keep track of it as we go from left to right. So first, what we can do is when we see some line like this, we'll see this line here. Before we get to this line, first this line ends. So initially we have, like, here are all of the vertical lines that are of interest, these 5 positions. But once this one ends, then in our sweep, we'll remove it from whatever data structure we're going to use to store these vertical lines. So we imagine deleting this endpoint here. Now effectively, we just have this big range here, this one, and then this one. Now we get to a vertical line like this, and we need to count how many regions does this create. It's got this one here, this one here, this one here, and this one here. These are the vertical lines it intersects. If it intersects 4 lines, that means it creates 3 regions. So we add this region here, add this, and add this. Then the next thing that happens, I guess I'll draw a different example instead. So we might also have lines that intersect this right point. They might be something like this. So now if we have a second vertical line, maybe one that's like this here, this one's interesting. It intersects 4 vertical lines, but this line here doesn't really count as like an intersection point because we don't create a region since these 2 are still connected. The reason for that is this doesn't have like a right endpoint to cut it off. So we won't actually add this to our list of like horizontal lines until we've already found a right endpoint for it. So the next time we have some edge, maybe we have a vertical line that's like this. First we'll count how many things does it intersect that are in our set. In this case we've got this one here and this one here. So we add 1 for this region. We've also just created the right or the left boundary for this horizontal line. And in that case, we can like increment the answer. So, or not increment the answer, but like add it to our set. So now we have this additional thing in our set. And then we can keep doing this from left to right. The one thing this won't count is, I guess, exactly what we have now, which is it won't count this region here, and this region here. So to do that, what I do is I just add 1 more line like this, and that'll count those. All right, cool. That is problem E. One last problem, which is problem F. Let's talk about that. And how do you do problem F? Well, here's the idea. Yeah, so the idea is just like you've got this segment tree basically, and then there are 3 different operations, I guess 4 different operations you have to do on it, but some of them are very easy. And we can like simplify it down to 3 operations, and then we can see that it's not really any operations at all. So the first one is range sum. We know how to do range sum on a segment tree. That's easy. The second one is point update. We also know how to do point update on a segment tree. That's pretty easy. You just walk down the segment tree, whatever point you need to update, you update that, and then on the way back on your DFS, you recalculate the sum for every node that's a parent of that. So if we modify this node here, then we update, or we recalculate the sum for all of these nodes. To recalculate the sum, you just look at your left kid, right kid, add up their sums, that's your new sum. All right, so we can do all of those things. The hard part is how do we swap and how do we reverse a certain section? So if we want to reverse all things that are of length like 4, for instance, really we can turn that into a bunch of swaps. So if we want to reverse things that are length 4, we can just swap these 2, make like the left the right and the right the left, so we just like invert them. And then we can do that for these ones as well. So now if we want to find the first element, instead of going left and left, now we go right and right, so this is the first element. The second would be you go left and right. Instead you go right then left, there's the second element, third element, fourth element. So as we can see, we've inverted this group here. You do the same thing for this group of 4 as well. So basically all we have is, now once we have this, we've converted reverses into do swaps. So like we've simplified, we've gotten rid of one of the queries because we can just do it as another query instead. All right. So now what we're left with is, how do you do these, how do you do left, right, like inversions? How do you do this swap? It's a bit tricky, but it's not that bad. It might seem a bit tricky for the following reason. You might have to like change a whole bunch of segment tree nodes, right? We might have to change all of these segment tree nodes, and there might be order n of them. So yeah, so it seems hard, but it turns out it's not that bad. And here's why. All of these things are always the same. Like all of the edges on this layer are always either going to be swapped or not swapped, which means instead of changing every node, we can just have some lookup table saying, are the edges on this level swapped? Okay. This is from a previous contest. Give me a minute.
Problem G got wrong answer test 6, sir.
All right. So for each layer, we can just say, is this swapped or not swapped? And yeah, then we can just change it in order 1. Then we go down our segment tree, we can say, okay, should I have this layer swapped or should it be not swapped? The one other caveat is usually for segment trees, I store the left endpoint and the right endpoint of some range, but it's easier just to think about it as like relative to the start of my range, where is this other range? So instead of like making your left and right endpoints like permanent and trying to modify all of those, instead you can just say, when you pass down this range, relative to me, if this is 0 and this is my length, this is my size, what does this other range look like? So if it's like this, instead of passing in, this is like 7 to 10, you pass in, well, this is 0, so this is 1 to 8 or something, I don't know. 1 to 8, 1 to 4, whatever this winds up being. Yeah, okay, so let's look at the code for that real quick. Oh, I never showed code for D. Yeah, code for D is not too bad. We have a bunch of events. Well, I guess I'll go over D code after in a bit. So this flipped is just like some global array for whether each layer is like swapped left to right. And then we build this segment tree. So then when we have all of these queries, if we have a reverse query, we swap all ranges less than the size we're supposed to swap. So it's just modifying that array. And if we want to swap some range, we just modify that particular entry in the array. Then we just call segment tree methods for the other two queries. So the entire problem is, how does the segment tree work really? And what I do is I store an array of the two kids. Index 0 would be what would normally be the left kid. Index 1 is what would normally be the right kid. And then I just like, when I want to see what is my left child, then I look on whether this layer is flipped or not. And if it is, then I look at the opposite thing instead of what I would normally look at. Point updates are pretty easy. Here's the one part that you have to be careful about, I guess, which is whenever you go into your right kid, you need to adjust the range accordingly. So you need to subtract out the size of your left kid, which is that. That happens in this other segment tree method as well, this range sum. When you go into your right kid, you need to subtract out the size of your left kid. Yeah, all right, that's problem F. And then problem E, well, I guess if you're interested in problem E, then you can pause the video and wait for it to be decent quality. But basically, here's the idea. We have a bunch of events, and the way I handle my events, the x coordinates come first, and then I have the delta. So if it's +1, that means you're adding a horizontal line. -1 means you're subtracting a horizontal, you're like removing a horizontal line. And y, you have the starting y and the ending y, y1, y2. So this is the line that I add at the end on the right side to count all of those groups that wouldn't normally get counted. And then I keep track of two things. I keep track of a Fenwick tree so I can do range sum to say how many horizontal lines are in this range. I also keep track of the integer of the lines I have that come from the right that I don't have a left endpoint for yet. in this tree set. So there are a couple cases. The first case is if I want to add a horizontal line. If the horizontal line is up against the left side of the wall, then I just add it right away. If it's not, then it's like something that doesn't have an endpoint yet, and I have to add it later. So I add it to my no endpoint set. If I'm removing it, now usually the logic would be more complicated. I would have to worry about the no endpoint set, whatever. But since it's guaranteed that they either touch the left side, the left wall, or the right wall, then it makes this easier. All I need to do is update the bit. And then at the end, stuff will be wrong, but it doesn't really matter because it won't ever get counted. Okay, so then the last part is for vertical lines. And I just count how many do they intersect in the bit. And then I also say, okay, for everything that they intersect in this no endpoints list, remove that thing from the list. It's kind of like a double-ended priority queue, basically. Remove it from the list, and then update that position in the bit, in the Fenwick tree. Yeah, that's it. So here's the Fenwick tree code. I guess you can look at that. You can just like look up how to do a Fenwick tree. So that's the contest. I thought the problems were pretty good. D, I don't know how I felt about, but the rest of them were good, especially E and F. They're both interesting problems. So thanks to the authors for a good problem set, and I hope you enjoyed it as well. I thought it was a good contest, so it was solid. Hopefully your rating went up if it was rated for you. And I guess that's all for today. So thanks for watching. Have a great day, and see you next time. Goodbye.